And let us do the examples of the underdamped systems first, and because here we have all the information here. So for example, we are given equation of motions 5x double dot plus 2x dot plus 50x equal to 0. And we are given the initial conditions x0 equal to 0.2 and x dot 0 equal to 2. So we're going to find is the solutions for this. So the first one we need to determine, well, it's okay. So we assume the, say, xt equal to a times exponent pt. So in this way, you can see the characteristic equations will be 5p squared plus 2p plus 50 equal to 0. Okay. So from here, we can solve for p. P will be equal to minus 0.2 plus minus and 3.156. So this is definitely an underdamped system because the characteristic root is a complex conjugate, and that is our case 3. Okay. And here we directly solve for the differential equations. So by tools, by mathematics, we know we always have the solutions. So right now we have this one. So this is the underdamped systems. So with those information in mind, maybe for the first time you can review from the beginning, but let me direct plug in here. So therefore, with this information in mind, and again, how to help ourselves to plug in information to this information here, again, let me highlight, this is the real part. And this is the imagined part. Okay. The information doing is this. The first one, we write the oscillation form. Oscillation form is in terms of the oscillation frequencies, right? Omega d. And what is omega d? We need to calculate. So here I'm kind of the piece by piece. I put in the related information. Omega d, by our calculations, is this one, omega n multiplied with 1 minus zeta squared. I need to calculate these numbers. And how can we calculate? To do so, we need to calculate omega n. So kind of the layer-wise. So from here, omega n, we can look at our system here. For our system, maybe let me review here. For our system, 5x double dot plus 2x dot plus 50 x equal to 0. So that means x double dot plus, I scale all the terms by 5, 2 over 5 plus 50 divided by 5. Okay, so again, you have scaled down and you compare to the standard 2 zeta omega n x dot plus omega n squared capital X equal to 0. So you compare the coefficient turn by turn. So from here you can see 50 divided by 5 equal to omega n squared, and 2 over 5 equal to 2 zeta omega n, right? So that is the first step. Whatever the information needed, we simply do the calculation. So from here, we can determine omega n. Omega n equal to square of 10. And that one is equal to 3.31, 3.16. Thank you. Okay, the unit is radian per second. So once we have omega n, we can determine what is zeta. So we have omega n, we simply plug in here, then we can determine zeta the zeta will be equal to 0.06. Okay. So with omega n, with zeta in place, we can determine omega d. So that simply is 3.162 multiplied with square to 1 minus 0.06 squared. Okay, so that numbers will give us a 3.156 because the damping ratio is so small. So, okay. And so let me again fill up the piece by piece. So right now we have 5, so let me write it up here, 1.51560 minus v here, okay? So now I want to fill up the amplitude. The amplitude basically is equal to this, the x multiply exponent of functions, and sorry, that term. These terms together are the real numbers of the characteristic group. So here is minus 0.2 and with t. Good? And again, I know I can write it up because we have derived the information there, and through our interpretation, we can right away to plug in the real part of the root. And that is going to here, and the real part is minus 0.2. So we can directly read information one by one into here. So we keep writing here. So this is minus 0.2t multiplied with x multiplied with this one. Okay. So again, we have this form, and let me call this equation 1. Okay. So using the informations, and if we do it carefully, well, can I leave this to you to solve for x and v? Because I didn't solve for this one. I didn't solve for xv in terms of this form. My solutions is this. I assume x of t equal to, rather than using cosine with this one, I'm using this one minus 0.2t. Again, this is this form, and with c1 times cosine omega dt plus c2 sine omega dt. If you expand this term, and if you expand this term using this information, cosine a plus b, cosine a minus b equal to cosine a cosine b plus sine a sine b, then you can have this form. Okay, and again, this form appeared when I think my solution is adopting this form here. So rather than solving for capital X and V, I solve for C1 and C2. So with these things in mind, and let me plug in the numbers with T and C1 times cosine 3.156T plus C2 sine 3.156T. Okay, so using the initial conditions, 0.2 equal to x0. So this one will be equal to C1. Okay, and then using the x dot, this information equal to 2. For these informations, I think you need to conduct what is x dot. let me set time. Again, this is x functions, and that is a multiplication of two time functions. So in this way, once you do the derivative on this, and you look at this one carefully, I think you need to do the chain rule, partial derivative. How to say that one? Right? Do you know what I'm saying? Let me do it. Let me do this one here, okay, and write it on the space. So d dt xt simply is equal to, you take the derivative on the first term, is minus 0.2, the exponent minus 0.2t. So this is the derivative of these exponential functions, right? And multiply with whatever we have, C1 cosine 3.156t plus C2 sine 3.156t. Okay, plus, then you do the derivative of the second terms. So right now I've done the derivative on the first term, and then I do the derivative on the second term there. So that will be equal to 3.156 times minus C1 sine 3.156t plus this one is C2 cosine 3.156t. Okay, good? That is a derivative, so that is the form here. So once you have that form, you simply plug t equal to 0 and then sigma equal to 2 and to solve for C2. So therefore you can have the C2 will be equal to 0.6464. So in this way we completely solve this problem. Okay? So that we can take that.